Okay, hello. I'm Albin Bernhardsson. I'm an engineer at ARM. I work with optimizing game engines for the ARM GPUs, as well as doing research into new technologies to help establish best practices. And fortunately, I was able to be here in person. So today I will talk about variable rate shading, or VRS for short, and how we can use it to improve our performance. So first, let's have a refresher on VRS, or an introduction for those not familiar with it. VRS is exposed in Vulkan through the fragment shading rate extension, and it allows us to control the rate at which fragment shading is performed. What that really means is that we get granular control over the performance and quality of fragment shading. So for instance, when using a 2x2 shading rate, what that means is that for every 2x2 area of the frame buffer, we will execute the fragment shader only once, and write the results of that one execution to all of those 4 fragments. That's not accounting for helper lanes. Rasterization is unaffected, as is blending, so they will still be performed at the full rate. We have several different ways to control the shading rate. All of these are optional, so make sure that they are supported on your device by checking the features struct. The first is pipeline shading rate, which is essentially setting the shading rate per draw call. Typical use cases for this would be using a lower shading rate on objects that are out of focus if you're using depth of field, or objects that are in motion if you're using motion blur, since we'll be blurring them anyhow, so you won't notice a reduction in shading rate. The second use case is setting the shading rate per primitive. Use cases here are not quite so clear. I can't really say I've seen many people using this, so if you are using this, I'd love to hear from you. And the third is what we'll be focusing on today, which is setting the shading rate for each tile of the frame buffer by using a screen space shading rate attachment. Typical use cases would be foveated rendering, or the focus of this talk, to adapt the shading rate by analyzing the frame contents every frame and generating a new attachment every frame. So how does this attachment work? Well, we divide the frame buffer into tiles. Each tile gets its own shading rate. Typical tile sizes would be 8x8 or 16x16 pixels. We store the shading rate for all of these tiles in a shading rate image or attachment, where each texel in the image represents one tile, and the value of that texel will tell us which shading rate to use. This shading rate attachment then becomes an input to our render pass. One important thing to note here is that when I say tile, I really just need a square area of the screen. So think tile deferred rendering, not tile as in a tile GPU that Pete Harris was talking about in his mobile best practices talk. We can use all of these different ways to control the shading rate in combination by using combiner ops. For instance, we can say, take whatever the maximum is for this particular tile by comparing the pipeline rate and the attachment rate, and then using the maximum. We have some trivial combiner ops, which are always guaranteed to be supported, and these are just keep one or the other. So use the pipeline rate or use the attachment shading rate without looking at the other one. So these are always supported, but if you want to use the non-trivial ones, which include the aforementioned max or min, then we need to check for support, and we do that in the fragment shading rate properties struct. This struct also contains some other important information, like what shading rates are supported. Some platforms support shading rates up to 4x4, others only up to 2x2. All shading rates have to be a power of 2, so 3x3 is not a valid shading rate. They don't have to be square, but they do have to abide by the maximum supported aspect ratio, which on every platform I'm aware of is 2. That means you can have a shading rate of 1x2, but not 1x4. And the final property I want to highlight, although there are many others in this struct, is how large is each tile when we're using an attachment. And that's up to the user to say, but you need to make sure that you are within the supported limits. So what's the case on ARM GPUs? Well, we're introducing VRS in Mali G615, Mali G715, and the Immortalis G715, so our newest devices that are out now. We support all the different ways to control the shading rate. We support non-trivial combiners. We support shading rates up to 4x4, maximum aspect ratio of 2. And we support tile sizes of 8 by 8, 16 by 16, and 32 by 32. So now that we know what that VRS is, how can we use it to improve our performance without having to sacrifice our visual quality too much? So to look at that, we'll be looking at this piece of content, which is a clustered deferred renderer. It has a fairly advanced global illumination technique, at least for mobile content, which also means that it's quite expensive. And the scene we'll be looking at is, of course, everyone's favorite. It's Sponsa. So the first thing to note is that we control the fragment shading rate. So obviously, it's going to help with fragment-bound passes. So passes with very simple or cheap fragment shaders are unlikely to benefit. If you try to apply VRS to your shadow map pass, you're not going to see an improvement because typically you wouldn't even have a fragment shader for most of your meshes. For our content, we identified 3 passes that could benefit, and these really are the 3 most expensive passes, and they are all fragment-bound. They are the Indirect Diffuse, the Lighting Pass, and the Indirect Specular Pass. The Indirect Specular Pass actually happens before the Lighting Pass, but I'll be going through them in this order. You'll see why. So the first is the Indirect Diffuse Pass. So what does it do? Well, it's a single full-screen triangle that renders at 1/4 of the resolution. It computes screen space, ambient occlusion, screen space global illumination, as well as sampling GI probes. This makes it an extremely good use case for VRS because, first of all, the fragment shader is quite expensive. We're doing a lot of calculations there, so there's a lot of potential performance uplift. The results are also very low frequency. So essentially, the incoming indirect diffuse lighting to any given fragment is a factor only by the world position of that fragment. The material data doesn't really matter. That means that the color changes very little between pixels unless there is a depth discontinuity. And this is why we can't simply do the entire pass at an even lower resolution, like 1/16 of the full resolution, because for most of the frame that would work fine, but we would get bleeding across edges. So we're going to generate the shading rate attachment to use for this pass, and we will calculate it based on these depth differences. So essentially, we can use a lower shading rate everywhere except where there is a depth discontinuity. There we have to maintain quality. So if there's a small difference, then we can use a low shading rate. Otherwise, we have to fall back to a higher shading rate. So to find what shading rates to use for a tile, we just have to look at the entire tile, look at the depth buffer, find the maximum difference in depth, compare it to some threshold, and if we deem it good enough, small enough, then we can use a lower shading rate. We will calculate the shading rate separately along the X and Y axes. That way we can use these non-square shading rates to get. So if we have an edge going along one axis, so we need to preserve the quality along one axis, we can still apply a lower shading rate along the other axis and get some benefit still. So how will we generate it? Well, we will use a compute shader that analyzes the depth buffer and writes out the results as a storage image. Writing to something as a storage image will disable AFBC, which is the lossless frame buffer compression that Pete went over in his talk about mobile best practices. And that usually saves us a lot of bandwidth, but here we will be disabling it. But in this case, it doesn't really matter because another thing that will disable AFBC is using an image as shading rate attachment. And also, the shading rate attachment is done at a very low resolution. Again, if we have an 8 by 8 tile size, that means it's 1/64 of the resolution, and it's a single 8-bit channel, so there's not a lot of bandwidth there to begin with. So each work group will handle one pixel in the rate attachment, and using an 8 by 8 tile size, that means it handles 8 by 8 pixels in the final frame buffer. Each thread then, to get an optimal work group size, handles a 2 by 2 region. It calculates the maximum difference in depth within that region, and then we share the maximum difference across the entire tile by using subgroup operations. We found subgroup operations to be much faster for this than doing a reduction in shared memory. Finally, one thread in the workgroup will compare this maximum value we got with the threshold we've selected and write out the resulting shading rate to the image. Finally, we can see the results of the pass overlaid with a visualization of which shading rates were used. So the red is 1 by 1, which is the most expensive. but also the highest quality. This is what you get normally if you don't use VRS. But we have some areas of the image where we can use a lower shading rate. So 4 is in green, is 4x4, which is the cheapest but lowest quality. So where there are depth discontinuities, we have to fall back, but we are able to use the lower shading rate in quite a few areas of the image. The next pass where we applied VRS is the lighting pass. This pass, again, this is a deferred renderer. So this pass will be reading the GBuffer and do all of the light shading for the direct lighting. And this is a cluster deferred. So this is really just a full screen triangle. We have no proxy light geometry. It will also composite the previously calculated indirect lighting. And in the same render pass, we will also render all transparent objects, which have to be done using forward shading. And we will composite volumetric fog. Basically, we will get all of our final rendered results before applying temporal anti-aliasing and tone mapping. So how can we generate a shading rate attachment for this pass, given that it does several different effects? Can we really find one attachment that works well both with light shading and the volumetric fog? The good news is that we don't have to do that. While it's only possible to have one shading rate attachment per pass, we can set the pipeline VRS and the combiner ops at any given point, which means we can enable and disable this one attachment we have for any given draw call. Since the main cost of this pass is the lighting draw call, we will generate an attachment that works well with that. And if it doesn't happen to work well with any other draw call, well, just disable it. So how do we actually generate this attachment? Well, we'll be looking at the finished lit results to generate the attachment. So wherever there's a low variance in the final color, there we can use a lower shading rate. The only problem is this is what we're trying to render in this pass. We don't have these results yet. So instead, we'll be looking at the ones from the previous frame. Now, anyone familiar with temporal techniques will object that we're going to have to do reprojection and probably a bunch of other error-correcting things, or else we're going to get ghosting or other horrible temporal artifacts. But in the case of VRS, we don't really get ghosting or similar artifacts. What we get is that certain areas of the image has a bit lower quality or a bit higher quality than we would have preferred. Higher quality is obviously not an issue. Lower quality is also usually not an issue, as it quickly self-corrects itself for the next frame, and it's not usually noticeable. But there are a few cases where we've been able to notice it, but for the most part, reprojection is not needed. And when it is noticeable, usually just upping the quality, say limiting yourself to only using 2x2 as the maximum shading rate, is usually enough. So how do we generate it? This is really just exactly the same thing as for the indirect diffuse. So we will use a compute shader to analyze, in this case, the lit results of the previous frame instead of the depth buffer. And same thing as before, work group handles one pixel, so one tile. Each thread handles a 2x2 region. We calculate the maximum difference within that region, share the maximum using subgroup operations, and finally, one thread compares it to a threshold and writes the resulting shading rate to the attachment. The only difference here is that instead of looking at the depth, we're looking at luminance. Or is that the only difference? There is one more significant difference, which is that in this case, the input we're using to generate the attachment has already had VRS applied to it. So if you consider a 2x2 region, well, if we used 2x2 VRS in the last frame, we wrote the same result to all of those 4 fragments. So when we analyze it this frame to figure out what shading rate to use, well, all of the pixels are exactly the same. The variance is 0. So of course we can use VRS this frame as well. We will never, ever use a lower or a higher shading rate ever again. We get a feedback loop where the quality degrades over time. So we need to combat this feedback loop. So to compensate for this, we expand our search slightly outside of the region that our thread would normally be responsible for. We add some additional pixels that we also check the luminance of and check the difference in luminance. And that way we are able to get rid of this feedback loop. Finally, we can see the results of the pass overlaid with the shading rates used. So we can see on these cloths that are very much one single color pretty much, hanging down, we can use a lower shading rate, but we can also use a lower shading rate in other parts of the image where, for instance, we have very low lighting, so there's a very low variance and we can't really see much detail in those particular parts. This raises a question. If we are using a lower shading rate in the lighting pass, do we really need to do the GBuffer pass at the full rate? Can't we just apply this attachment there as well? And we absolutely can, but there are some considerations. One thing is that when you have fewer fragment shader invocations, they will be spaced further apart, which will affect your derivatives. This will in turn affect which MIP level you sample when sampling any MIP map texture. And that's going to lower your texturing quality. That can be quite noticeable, actually. We can compensate for this by reading the shading rate in the fragment shader. There's a built-in variable to do that, and add a MIP bias whenever we're sampling a MIP map texture. This does add another shader variant, so if you're already suffering from shader variant explosion, this might be an issue. In our case, our GBuffer pass is extremely simple. The fragment shader doesn't really do all that much calculations. The only real calculations is normal mapping. Other than that, it just samples some textures. So we didn't actually see any significant uplift applying VRS to the GBuffer pass, so we decided not to. But if your GBuffer pass is more expensive, it does more calculations in this pass, then it might be worth considering. Finally, we have the indirect specular pass. This pass draws a single full screen triangle at 1/4 of the resolution and calculates screen space reflections and combines it with sampling reflection probes. So for this case, we tried to generate a good attachment, but found it was actually quite difficult. Either the results from analyzing the GBuffer was not very high quality, or it was very expensive to generate the attachment. So in the end, we decided we're just going to use the same attachment as we did for the light shading. But this pass is done at 1/4 of the resolution, so first we need to downscale it. So we use a compute job to do that. This compute job, each thread will simply read 4 texels, see what the maximum rate is of those, and output the results to the downscaled image. This gave us acceptable quality, and the downscaling is practically free. So here's an example where we start with the lighting, the attachment used in the lighting pass, and then after we downscaled it, we do lose out on VRS in quite a few areas of the screen, but we are still able to use a lower shading rate in some areas. So it's still overall a win. It's not a huge win, but given that the generation of this attachment was essentially free, a free win is a win. And finally, we see the render results along with a visualization of the shading rates used. So, performance, how much do we actually gain? So we measured performance on an Immortalis G715 device at a target resolution of 1080p with a bit of unusual aspect ratio, but in the mobile world, these kinds of aspect ratios are not really that unusual. You don't usually get 16:9 phone screens. We tested using both 8x8 and 16x16 tile sizes. One important thing to notice there is that when using the 16x16 tile sizes, we also have to modify our compute shader that generates the attachments a bit so that we still get the optimal workgroup assignment and are able to use subgroup operations to share the data across the workgroup. We also tried limiting our shading rate to 2x2 or going all the way up to 4x4. So first of all, here are the GPU active cycles. This is the counter that is most closely associated with frame times. The baseline is not using any VRS, so everything as at a full rate. In yellow, we have using tile sizes of 8x8, and we're able to see quite a good performance improvement here, given that this is for essentially no noticeable visual quality impact. That's essentially a free win, right? In orange, we have the same thing, but tile sizes of 16x16. Still a very good performance increase, but not quite as good as 8x8. And the reason is, whenever we find a single value that is above our threshold within a tile, we have to essentially fall back and use a higher shading rate for the entire tile. When we have a smaller tile size, that means we have more granular control, which means we have to fall back less. And so we're able to use a lower shading rate in more areas of the screen. As we can see, we also get a slightly higher performance benefit when using 4x4 VRS compared to 2x2, but it's not a very significant improvement. Part of the reason here is that we've been quite conservative with our thresholds. We don't want noticeable quality degradation, so we aren't able to use 4x4 in that many areas of the screen. If you're rendering at 4K, probably you're able to apply 4x4 more. But of course, as we've said before, performance is not just about frame times and cycle counts. We also need to consider bandwidth, and here we don't really expect VRS to improve much. For the read bandwidth, we are doing fewer fragment shader invocations, which means we are doing fewer texturing instructions. Unfortunately, that doesn't necessarily translate into lower bandwidth, as we will mostly be sampling the same cache lines anyhow. This obviously depends a bit on your content and what your pass does, but for these passes that we've applied it to, it's not a significant improvement. In fact, we have introduced additional passes to generate these shading rate attachment, and these incur a read bandwidth cost of their own. So we actually end up increasing our bandwidth slightly, but it's not a significant increase in bandwidth, especially not when compared to what we're saving in frame times. And finally, there's the write bandwidth. Here, we don't really expect VRS to have any impact at all, since while we are doing fewer fragment shader invocations, we're still writing out exactly the same number of pixels. But we are writing out more of the same pixel, which means that the frame buffer compression is able to do a slightly better job. But overall, not a big saving in write bandwidth. So in conclusion, you can apply VRS to improve your performance of fragment-bound work. The savings apply to cycle counts, not so much to bandwidth. With well-chosen heuristics and well-chosen thresholds, you can minimize the impact to image quality, even to the point where it becomes unnoticeable. When using the results of the previous frame to generate your attachments, you don't usually need to do reprojection, but you do need to be very careful about introducing feedback loops. Finally, I'd just like to remind you about checking out the ARM developer program, and also to check out our table out by the entrance, by the registration. If you want to see any of this running in action, we'll have some devices, and you can see the VRS demo and see if you can spot any difference when it's enabled or disabled. That's a challenge. You can also see the ray tracing demo that Jose Emilio will be talking about more later in the week. Thanks, and any questions? Yeah.
So nice trick with the temporal stuff feedback. I was wondering, do you ever see any kind of drawback or artifact from the fact that the shading rate image is kind of aligned to tile boundaries? And if you look into jittering that about, kind of right up.
Yes, so
repeat the question.
Sorry?
Let's repeat the question.
Oh, sorry, yes. So the question was if we see any artifacts from the fact that when we do use the previous frame to generate the attachments, we essentially align ourselves to the tile boundaries. So do we do some kind of jittering between frames when generating the shading rate attachment? And so we do see artifacts sometimes, but one thing to note is that for the indirect diffuse pass, we are using the depth buffer of the current frame. So for that, it's not an issue. For the cases where we do reuse the results of the previous frame, again, we introduce this extra pixels outside of the tile, and that helps us. In addition, we are also using temporal anti-aliasing, which means we are actually jittering. I haven't actually tried disabling the temporal anti-aliasing and see what happens. I don't know. Maybe that helps, the fact that we have a jitter there. So possibly. But yeah, the fact that we have a jitter and the fact that we compensate for this feedback loop by adding additional samples outside of the tile, that certainly helps. Yeah?
Just wondering about bearing shaping rates in VR application. I can imagine that generating such an attachment would be pretty straightforward because we have a circle like a view and some stuff where user is looking at. But maybe you have some tips how to apply this technique based on a VR application where we do have some inputs from the application where to look at, where to generate the most valuable.
Yeah. So the question was about using VRS in VR applications, and as mentioned, typically you would be looking at where the user is looking. If you have some kind of eye tracking or have some kind of data about where the user is looking, then you can generate the VRS like shading rate attachment very simply by just, well, where the user is focusing, that's high shading rate, everything else is low shading rate. It's not really something we've been looking at, so I don't really have any tips there, but yes, that should work well. Yeah. Sorry?
How much development time did it take you to educate the sample about VRS?
Yeah, so the question is about how much development time it took to integrate VRS into our sample. And so integrating VRS is, if your renderer is set up to do all this already, then it's not that complicated to do. Again, pipeline VRS is very trivial to implement, I'd say. Shading rate attachment, a little bit more complicated, but really it's not a lot of work to integrate it into an existing engine. It doesn't really affect your rendering pipeline all that much. You just need some way to generate this attachment and then specify it as part of your render pass. So it's fairly simple to implement, fairly simple to add to an existing renderer and implement. The main thing is just figuring out how do you generate this attachment. That's the main thing. And fortunately there, well, you can take a look at these examples, and there are also similar examples doing similar stuff by Microsoft, AMD, and NVIDIA, which all have presentations on this. So fortunately, you don't have to do all of that alone. And it also really depends on what you're trying to apply it to. So again, we had a very different technique for our lighting pass than for our indirect diffuse pass, where we looked at the depth buffer instead of the luminance. And in all of these cases, the shader for generating these is really quite simple. Like compare the difference in depth, that's extremely simple to do. Compare it to some threshold value, again, really simple. So I think the main thing that took development time was really making this work across a wide variety of devices, because when you're using subgroup operations, what is optimal for the particular platform you're running on varies a lot. So we need to end up having a couple of different variants of the shader that generates the attachment. And I think implementing those different variants and finding something that works well across all platforms, that's really the thing that takes the most time. But overall, it was not a huge amount of man hours going into this. Any more questions? Okay, thanks very much.